Hello all, welcome to virtual APS this year. I'm sure it's weird for many of you, but I hope you learn a lot. Hello, I'm Pranav Mohan, and along with Dr. Sadiq Dabiri, we are from Purdue University, and we are presenting on cavitation bubble growth in a Rankine vortex. A sample animation of the bubble dynamics that we are trying to analyze in the Rankine vortex is shown on the top left of the screen to give a brief introduction about the cavitation bubble dynamics. Cavitation can hinder various engineering applications in the form of noise, vibration, erosion, and reduced performance. And that is why we need to understand every aspect of it from both dynamics and other parts. However, we are interested in tip vortex cavitation, which can be considered as a canonical problem, which represents various other physical phenomena as well, and can be found in various applications such as turbomachinery and blade surfaces. Now, if the circulation velocity of the vortex and the radius is very small, and the velocity is very high, the pressure at the core of these vortices can be very low and sometimes even be below zero. And if any nucleation sites are present in these cavitating vortices, they would, due to the huge pressure difference, they would cavitate. And this is the cavitation bubble dynamics in terms of growth, splitting, and collapse, which is not well understood and what we are trying to study. There are various other factors such as water quality effects and surface roughness of the blades or hydrophiles that also play a role, but those are not analyzed here and can be found in other studies. Now, vortex formation is a fundamental in turbulent flow, and studying vertical cavitation may give us more insights into turbulent flow as well. So this is the motivation for studying the bubble dynamics. So what we are interested in is studying a single bubble dynamics in a Rankine vortex. So to provide a brief literature overview of it, Choi et al. In 2009 used axisymmetric conditions to predict the cylindrical shape during the growth of the bubble. And basically they modeled the growth and the collapse of the bubble as two separate processes, and then combined those simulations and the results. Now, the dynamics inside the bubble have not been very well explored, and that's because the density of the bubble in comparison to the fluid around is much smaller. So in terms of the dynamics inside, the influence is smaller. However, the bubble and fluid interaction plays a big role in how basically cavitation occurs. If obviously the pressure everywhere around the bubble was uniform, it would grow spherically. However, we here observe a cylindrical bubble growth. During the collapse of the cavitation bubble, we can also expect to see various re-entrant jets formed, which has not been explored as well. Choi et al. In 2007 also analyzed vertical cavitation through experiments, and a time sequence of their captures of their snapshots have been shown here to basically demonstrate that, yeah, we do observe cylindrical bubble growth. So we do a direct numerical simulation using an all-max solver on Basilisk. We solve the continuity and momentum equation with the viscous stress tensor and include the surface tension effects. We also solve the internal energy equation, and to close the system, we have an equation of state relating the pressure and density. Here, B for air is considered to be 0, and B for water is considered to be 3049.13. We tested our solver for various test cases, and we found that this empirical value fits the best with our solver. For the computational domain, we use a cubic Cartesian grid with the length on each side of about 800 mm. The axisymmetric velocities given of the Rankine vortex are given as this. However, when they are transferred to the code, they are in Cartesian coordinates. Similarly, the pressure in the vortex and in the domain is given through this equation, and we have the equation of state as it was mentioned previously. So the simulation parameters that are necessary to model the problem are the cavitation number, which basically represents which is given by the pressure of the bubble, the vortex radius, the far field density, which is the density of the water and or any other fluid that we might use, and circulation velocity squared. So we also have the bubble to vortex size ratio, which is given by radius of the bubble over the radius of the vortex. We have the aspect ratio. So the simulation that we are analyzing today is axisymmetric. However, we're not restricted to axisymmetric solutions. However, since it's axisymmetric, we can define an aspect ratio, which gives us a radius in the x and y direction, and in the z direction, we get half axial length given by L. So through a ratio of that, we can define that as the axial length. As mentioned previously, we can change the surface tension. However, it was considered to be constant at 72 millinewtons per minute. To give a brief flow visualization, as mentioned previously, if the circulation velocity of the vortex and the radius, if the vortex velocity is high and the circulation and the radius of the vortex is small, we can get negative pressures, and that can elongate and grow the bubble axially. The bubble dynamics can be divided into 4 different stages, given by initially the growth, then pinching from the radial direction, which leads to elongation, and finally fragmentation towards the end. However, due to the time constraint, only the growth of the bubble will be analyzed, and the growth of a single bubble can be seen here. Important points to notice here is that the radius of the bubble basically fluctuates from a maximum to minimum. However, in the axial direction, the bubble continues to grow continuously. So the growth of the bubble is mostly in the axial direction than in the radial direction. But before we actually place the bubble in the simulation domain, we have to first measure if the vortex defined can diffuse over time correctly or not. So here, the vortex velocity at the radius of the vortex is plotted, and it's seen that the velocity over 10 milliseconds reduces by about 80% in the for different cavitation numbers that we ran. The cavitation number here is 1/200. Similarly, the pressure also is -9 bar to start with, and then it increases as the time passes by. To analyze basically the pressure in the domain, here the pressure along the x-axis is plotted, and it's seen that for different time steps from 0 to 10 milliseconds, we see that the major change is basically at the core of the vortex, whereas on the side of the vortex, the pressure remains same. So it's the core where the pressure is changing. So next we want to look at the effects of the cavitation number, and it is seen that, and in this plot, we have the volume over the initial volume of the bubble in non-dimensional way. It is important to notice that the y-axis is in a log scale, and we plot for different times here. And we see that as we decrease the cavitation number, actually the growth that we get, the volumetric growth that we get of the bubbles can be in the order of 2 to 4 orders of magnitude from where it started, depending on what the cavitation number is. And just the difference in volumetric growth that we observe between the different cavitation number, there is an order of 2 difference between the growth. So what is important to observe here is that we are getting a substantial amount of volumetric growth. However, this growth, as we saw in the animation previously, is mostly in the axial direction than in the radial direction. So next, the aspect ratio over time of the bubble is plotted, and it can be seen. So aspect ratio again is given by the radius of the axisymmetric elliptical bubble divided by the half axial length of the bubble, and it can be seen that for the lowest cavitation number, we get the least aspect ratio, which means that the growth along the axial direction of the bubble is the maximum in the lowest cavitation number, and it's the highest in comparison for the larger cavitation number. And again, it is important to notice that in all the cases, the growth in the axial direction is much more, which is why the aspect ratio is less than 1. Finally, we also wanted to look at the effect of the initial bubble size. So we have the initial bubble as RBV is just the vortex radius of the bubble to the radius of the vortex ratio. And we basically plot 3 different initial bubbles sizes as 1/20, 1/10, and 3/20. And we look at a cavitation number of 1/200, and we observe that for the volume, then the way we normalize volume here is using the middle case where the RBV is 1/10. And we observe that even though the initial conditions of the bubbles are different, they all lead to the same solution going here, and the solutions basically converge. Similarly, we also observe that the aspect ratio also does not remains constant for the 3 cases that we are looking at, suggesting that the bubble dynamics that is taking place in the tip vortex cavitation is independent of the initial bubble size, or the bubble size to the vortex ratio. So to conclude, variable density Navier-Stokes equations are solved to model tip vortex cavitation. The growth of the bubble is strongly dependent on the cavitation number and the vortex core pressure. This growth that we get is actually much larger in the axial direction, whereas in radial direction it oscillates. And the size of the nucleation site that we get actually does not affect the bubble dynamics that we are studying. So I just want to say thank you all for listening to this presentation. Please leave your questions in the chat, and I'm looking forward to interacting with you all in this session and in others later. Thank you very much.